well. Now we still stop to investigate anything, and we're waiting for something happen in the U.S. as well in terms of the asphalt research. And now when the word of the super PEF being announced, that we very curious. Should we change, or should we still stick on the Marshall and all that? We would like to know your view about this one as well. What should we go about the direction in terms of the mixed design?
Yeah, thank you. In the United States, there's a saying that if it's not broke, don't fix it. So I would personally I would say that let us look at the problems that we have here, and can it be addressed, still addressed by using the Marshall mixed design method. Okay, so you want to look at the problems that we are facing here. Do we have a rotting problem? Do we have a cracking problem? And with the Marshall mixed design method, can we adequately address those problems? Okay. So the main problem with the Marshall method is the compactive effort. If we cannot compact a mixture that could simulate the field condition, and you test the mixture, so even if the mixture performs well in the laboratory, it may not perform well in the field. Right? But sometimes, and Marshall method been used for a long time, and even though they don't simulate the condition very well, it worked to some extent. So we want to, I would look at whether or not there is still a problem. Is the problem due to mixed design, or is the problem due to construction? Sometimes it may be due to construction, the quality control. If it's properly done, is the problem still there? And so my guess is that the compact, now we're dealing with heavy traffic, and the Marshall compaction may not be adequate because you're compacting the aggregate, and the aggregate get crushed, and very difficult to simulate the field condition. But initially, I would see if the problem could be solved by the Marshall method the way it is. Okay, and so we compact the mixture using the Marshall method. You have the specimen. Now let's test the specimen, not only with the Marshall stability, but we can run some other tests, indirect tension tests, and measure DCSE and other properties, and try that first without changing the whole system. If it cannot be addressed, maybe we need to go with the gyratory compactor. I started working as a university professor 29 years ago. I was a young assistant professor at the University of Florida, and at that time there were some problem with concrete pavement, so I had an opportunity to investigate some problems with concrete pavement. And so I want to share about my experience and my investigation of causes of problems with concrete pavement. Well, in Florida, they started constructing an interstate highway in the northern part of Florida in the early 1960s. Okay. As you recall, I've shown a map of Florida, but in the northern part of Florida, there's an interstate highway called Interstate 10 that goes in the northern part of Florida, and it's about 560 kilometers long. It stretches from the Alabama to Florida border. It crosses to the state capital of Tallahassee, and it goes east to Jacksonville. So it's about 560 kilometers long. Before they started constructing that interstate, there was a big debate between the concrete industry people and the asphalt industry people. And the concrete industry people thought that that road needs to be constructed with concrete, and asphalt people, of course, thought that it needs to be constructed with asphalt. And so finally they come up with a compromise. Half of that road was going to be concrete and the other half asphalt. Okay. And when I got to the University of Florida in 1982, I noticed that there were some problem with concrete pavements on that road, and so I got a chance to investigate as to what the problems were. Okay. Well, at the beginning, when they construct that concrete highway, this was the design used. It had 23 centimeters of PCC, means concrete, Portland cement concrete. And underneath there's a stabilized subgrade. And basically, it's a subgrade soil which is mixed with some asphalt emulsion to make the stabilized subgrade. Okay. And this was designed according to the Assoc Pavement Design Guide. Okay. However, there were pumping problems. The pumping is the erosion of the sub-base material and creating voids underneath the slab. Okay. And this is caused by inadequate drainage. Water could not drain away, and it was trapped underneath the slab, and so when vehicles went over it, they got pumped out, and this problem is called pumping. Okay, when the material got ejected from underneath the slab, it brings with it the sub-base material, and after a while, it creates some voids underneath the slab. And the problem was because there was no sub-drainage system installed in that pavement. So even though, if I go back, even though this pavement seems to be adequately designed according to the Assoc design guide, there was no drainage underneath the pavement. So when water got underneath the slab, there was no way out, and the water was trapped underneath the slab. And when vehicles go over it, the water got pumped out from the edge and the joints, and pretty soon there's voids. And when there's enough voids, it cracked because the slab was not properly supported. So I read into the history as to what happened when they found out that they had the problem. When they found out that they had the problem, they changed the sub-base design. They thought that, well, the sub-base was not strong enough. What if we improve the sub-base, make it into an even stronger material, then it wouldn't be eroded away. So they changed the design to this design. The same thickness, but have, instead of the asphalt stabilized subgrade, there's two layers, one layer of cement treated and then one layer of lime treated sub-base. But unfortunately, no sub-drainage system was installed, and the problem actually got worse. Okay, this material, even though it's stronger, it is less drainable. Water got trapped underneath the slab even more, and there's no way for the water to get out. And so there was even more cracking. And here, you know, with the stronger subbase, the pavement actually performed worse. And now they finished the construction of this stretch of highway with some problem showing up. And the next highway that they constructed was in the south. It was a highway that goes north and south. It's south of Tampa. This was a I-75 in Sarasota and Manatee County, which is south of Tampa. Okay. And so because of the problem on that previous concrete highway, some changes were made. What was the change? Well, the cement-treated subbase was found to be eroded, and so they made the subbase even stronger. So an Econocrete was used as a subbase now, and because it's a stronger subbase, it's called base. Okay? In concrete pavement, if the subbase is strong, you call it base. Okay? Otherwise, you call it subbase. So we have a base, a strong base, okay? Econocrete, and but unfortunately, no sub-drainage system was installed. If we had installed a sub-drainage system, the problem wouldn't happen. And some additional design features was also used, including a skew joint. Okay? So the joint was cut at an angle, and the idea was that if it's at an angle, when the actual load go over the joint, only one wheel would cross over the joint at one time, and so there would be less of an impact effect. But it turns out that it didn't work very well because with the skew joint, some angles were smaller. We have an acute angle, and the stresses in this corner were actually higher, and we had a lot of corner cracks. Okay? And in addition to that, they also they use a variable joint spacing of 15 foot, 16 foot, and 22 and 23 feet, different variable joint spacing. And the idea was that, well, when you have variable joint spacing, when a truck goes over it, there's less of a problem with synchronization. And so they thought that, well, if you have different joint spacing, you wouldn't have a synchronization effect, and this impact effect would be lessened. But it turns out that the longer joint spacing were too long, and we had a lot of transverse cracking on the longer slabs. Okay. It also had Econocrete shoulders. Okay. But we had, soon after this road was open to traffic, transverse cracking were observed, and the transverse cracking occur on the longer slabs. Okay. Well, according to the traditional way of calculating the stress, the cracking shouldn't occur in this fashion. Okay. And there's also pumping, and which was came as a surprise because they thought that the Econocrete was not non-erodable because it's much stronger, but yet there's signs of pumping. And when they collect the material coming out from here and analyze it in the lab, they found out that the material actually came from the Econocrete base. So we cannot have a non-erodible base. Okay, so water damage is very serious. Whenever you have a lot of rain, there must have a system to get the water out, no matter how strong your base is. Okay, so in 1982, when I was much younger, so I worked with Florida DOT's staff to investigate the problem. We check out dowel bars, check out drainage, and there was no problem with the surface drainage. The problem was with the sub-drainage. Okay? If the water could run out fairly easy on the top, but whatever that got underneath the slab, there was no sub-drainage system to get the water out. Okay. They also run FWD tests. And one of the things that puzzle us is why the longer slab cracked into half. Okay, and if you run the stress analysis the conventional way, there was no difference in stress, whether the slab was longer or shorter. The stress is the same. Okay, but if we consider the temperature effect, there might be a difference, and in fact we found out there's a great difference when there's temperature effect. We didn't know what the temperature was, so we collected some data on temperature. We drill holes to different depths of the concrete slabs. We insert thermocouples and connect them to plotter. 20-some years ago, we didn't use computer as much, so it was connected to physical plotters. And we got plots of temperature versus time at different depths of the concrete slab. And we got this type of temperature distribution. And this is a temperature distribution at different time of the day. Basically, this represents temperature at the top and temperature at the bottom. This is 1 inch below the top. This is 8 inches below the top. And we found that in the middle of the day, the temperature at the top is much higher than the temperature at the bottom. And this temperature plot changes, changes with time throughout the day. But what we found is that the temperature is much higher at the top than at the bottom in the middle of the day. At night is the other way around. At night, the slab is losing heat, and we end up in a situation where the temperature is much lower at the top than at the bottom. Well, what kind of effect does this have on the pavement? Well, conventionally, we analyze the pavement as if it's perfectly, it's well supported by its foundation. Okay. But at night, when there's this type of, when the temperature is lower at the top, it may curl up this way. And the middle of the day may curl up this way. And now the length of the slab has a great effect. Okay. When the slab length is longer, under this condition, when you put on the same load, the stress is much higher. Okay. And this was not considered before. Okay, so we developed a finite element program to do this type of analysis. So instead of calculating the stress under a normal condition where there's no temperature effect, now we do the analysis with the temperature effect. So we do the analysis in the condition in the daytime. Typically in the daytime we typically could have a temperature difference of plus 20 degree F or about 11 degrees C. Okay, it's hotter at the top than at the bottom by 11 degrees C. Okay, now with this temperature difference, this represents a slab and the two adjacent slabs, and this represents the axial load. So we put the axial load at the center, we get a plot of stress due to that load. And at that position, we put the load near the joint and get a plot and put the load near the corner and then also near the edge. And it turns out that when we have a positive temperature differential, now which represents the middle of the day, this represents the most serious condition. Okay, okay. So the stress under this condition is much greater than when you don't consider temperature differential, and the stress is actually about twice as much. So this is, and so the slab length becomes significant, and this explains why the longer slabs will crack in half. And we analyze the night condition as well. At the night, the magnitude of the temperature difference is not as big. So typically in the daytime we have plus 10 degree F. At night we have negative 10 degree F, about 5.5 degree or 5.6 degree C. Okay, so we do the similar analysis, put the low at the center, put near the